Okay, so the recording has started. I can go on the page and start fresh. Okay, so cool. So DC motors. So I started recording. So DC motors or DC generator could work both ways. It doesn't matter which way you started, but in the exam, they will most likely give you a DC motors question because they could have say more based on the motor side and the generator side, right? So just keep that in mind. So the DC motor itself, in terms of its operation, all it is really is that you have a current that's will go through the flow. Before I go into the deep details, you have a current. When you pass that current through a coil, the coil produces a magnetic field. Yeah, and that magnetic field, when it cuts another magnetic field, it induces a EMF because you have the Fleming's left hand. You have already set out your thumb going up, your index and your middle finger. Yeah. So based on that law, you end up with a force, and that force will basically on one side it will go up, and the next side it will go down, and it will just that's literally all the DC motor is. There's have no other ways for that's how it does work. Electrical giving you mechanical. The generator parts, the mechanical giving you back electrical. It's the same power flow, just a different starting point. Okay, so I look this. So you have a node pool, you have a sub pool, and this is a permanent magnet. So a permanent magnet means it will give me a permanent magnetic field that wouldn't change. It's just a magnet, nothing gonna happen. Right? So this here, you call these things right in this place, you call it flux, which is 5, which is your flux lines. This and this, you call them poles. Okay, so there's a 2-pole motor right now. Okay, so in this pole here, you have a magnetic field, which is cool. What we want to add is a coil. We want to put a coil in it. So to keep it simple, just use an easy coil. So it will just be this. Just to keep it simple. Obviously, in the actual motors, there's millions, hundreds of this one pattern here, because obviously one coil wouldn't be able to induce the EMF that you want to induce it. And what you're gonna do, just to remove the commutator, add a commutator. I ain't gonna go too in depth because I theory. All that does do is basically when something turning, you have to keep contact with the metal in order to keep current flowing in the same direction. If you end up turning and the current stop, the EMF gone stop, and the whole motor gone stop spinning. So what the commutators is when it have different type of commutators, like the brushes and slip rings and stuff. Basically, what those do is just keep the current flowing in the coil. That's to keep it simple. It just keeps the current flowing in the coil, which then keeps the induced EMF there, which then keeps the motor spinning. Because without the current, you have no induced EMF. And if you have no induced EMF, you have no spin. Nothing gonna happen. So we gotta add a voltage. So when we add this voltage, just to keep it simple, the voltage gonna give you a current. And when that current works in the circuit will actually produce its own magnetic field. So the magnetic field will just be like concentric circles. It will be little circles. Obviously, I draw in a top view. So actually, it will just look like this because actually going into the paper and coming out. Okay, so obviously, I draw it in a way that you can actually see the current flow. So the currents will actually be going around like this into the paper, out to the paper. But either way, so all we need to do is use the Fleming's left hand rule, and your thumb does point in the direction of the force, your index finger points in the direction of the magnetic field. So if this is your thumb, I mean your index, this will be the north pole, and the south pole is where you'll be pointing to. So you're going north to south. Your thumb will just obviously be pointing like this way, and then your index finger will be pointing like this. It'll kind of, well, the middle finger will be pointing to you most of the time if you're using it. So in the default position of your hand, your middle finger will be pointing to you. If you're using your left hand, the index finger will be pointing to your right hand, and the thumb will be pointing up. So all you need to do is just align those three things in the direction you see in here. So the first thing is the current going, in this case, into the paper. So you just point your middle finger away from you, because it's going into the paper, and the magnetic field still going from north to south, so your index finger should still be pointing from left to right. And in this case, once those two any position it need to be in, your thumb should be pointing down. So therefore, the force on this side of the coil will actually be pulling it down this way. And on this side, the same concept. Now the current direction has swapped. And if the current direction swap, if you align your fingers, the force on this side will be going up. So that's realigning your fingers, because now the current direction swap. The magnetic field is still in the same direction. It's just your middle finger changing direction based on how the current flowing. And obviously you're seeing this force going up and this force pulling it down, you will end up with rotation in this direction. Yeah, and you just keep spinning like that. And you can trace back. If the current stop, the force go and stop. And if the force stop, it just go and stop spinning. Or it wouldn't be spinning at the same speed. The speed will just drop, which you don't want. You want the speed to be constant. So that's to run it back through again. You have a voltage. Once you supply the voltage, it will create a current in the wire. And that current in the wire, based on this, one side will be flowing in one direction and the other side will be flowing in the other direction. Reason being is because you need the forces to be going in the opposite direction to turn. If both of the forces going in the same direction, like nothing will happen. You need one to go up and one to go down for it to spin. Okay, kind of self-explanatory. And once you use the Fleming's Lafond rule, you end up with the forces based on the direction of the path. Once you have that, that's basically the operation Fleming's Lafond. Cool. So just to add one more thing. So you end up with a concept called the back EMF, which is exactly what the word says. It is a back EMF. So that's how it does look, right? And follow me. This voltage is very high. The resistance of your armature is very small. So RA is literally like 0.18 ohms, etc. It's very small. So for the back EMF, the first thing we need, so you have the current, which is the inrush current. That will be your supply voltage divided by your RA resistance, because RA is very small. And if you have this is 230 volts and stuff, and this is like 0.18, it's very, very small. Okay? If this is small and this big, you end up with a large inrush current. If that large inrush current can actually destroy the entire machine. So what actually protecting the machine from this large inrush current is your back EMF. And this back EMF comes from something called Lenz's law. So that induced EMF will actually oppose the change that causes it. It's like if you're lying down and somebody call you, you're not gonna want to come up one time because you was lying down. That resistance to change is Lenz's law. So the moment you put on this voltage and that high inrush current starts, your back EMF will immediately start to develop because they're trying to resist that change that causing it to try to resist. So that's the reason why in the lab, when you was turning up the button, we told you not to crank it up too fast. Because if you crank it up too fast, you're not giving the motor enough time to build up that back EMF to protect itself. So as the inrush increases, the back EMF also increases. But it doesn't increase at the same rate, so you need to give it some time to build up. And once the back EMF builds up and it's strong, you could crank it up. Because at that point, the back EMF is enough to control this large inrush current. And the inrush current will actually be less. It will actually drop. Okay? Because it's like you're trying to, if I'm maxi full, it's not going to take in any more people in it. So if this back EMF large, the current that it's attracting will actually drop to an acceptable amount. And I think you all saw this with induction. When you cranked up the variac, the current just skyrocketed up. But as you continue to turn, the current dropped and it stayed at an acceptable value, which is why we told you all for that I want to crank it up, crank it up, because in an induction it's just a squirrel cage bar. But it's the same concept. That high inrush current in the induction motor, it have no back EMF there, so it have nothing to protect it. It have nothing there, just bars. But for the DC motor, you have the back EMF there to protect itself. So to use it, you need to crank it. To crank up the voltage slow, so the back EMF can develop to protect it from the inrush current. So the purpose of the back EMF is to protect the DC motor from the large inrush current. Why have a large inrush current? Because the RA resistance for the DC motor is small. So a voltage divided by a small value will give you a large inrush current. And this large inrush current could actually destroy the motor because current is heat. Heat is melt, burn, fire, right? So you need to give this time to develop, right? So this actually protects. Is the back EMF is basically the EMF induced based on Faraday's law. Yeah, because Faraday's law from here, passing current through a coil, it will induce an EMF. We know that. But the coil itself will induce an EMF to oppose that change. So don't mix up the two. The first one is the EMF induced. So when you pass current through the wire, you will get an induced EMF. Yeah? But the back EMF, that EMF, which is why they call it the back EMF, which is the reverse, he will also develop an EMF to limit or to control this induced EMF. The same example, you're lying down, you're lying down. If somebody call you, you're going to try to resist that, but you're lying down. In this case, something inducing, but also, why you induce it? It will actually induce something to control it or to bring it back to whatever it was before. But obviously, as this starts to increase, it will limit this. Because logically, when this EMF is induced, the current is high, which means that the back EMF is at its highest. As the back EMF starts to increase, just like a maxi, the current that it's pulling from the source will decrease. And if the current that it's pulling from the source decreases, this number 1 here, the EMF induced due to that current, will decrease. Yeah? So the entire motor will just protect itself. One is what you cause, and the other one is what you cause because of that thing you change. So don't mix up the two. This is the back EMF, which we normally call E8 in textbooks and stuff. This one you don't need to calculate, but just know this is due to Faraday's law. And this E is due to Lenz's law, or Lenz's law, by theory. Cool, so I think I spent enough time on that. So any exam, the first thing you need to know how to do is basically the EA, or the back EMF equation. That's the first thing you need to understand deeply, because majority of the time the questions will require you to calculate that in some shape or fashion. Okay, so I go through the back EMF equation. And we can stop now if you have any questions.
Excuse sir,
Yeah, go ahead.
it's how somebody trying to get Latin into the meeting right now.
Yeah, that's why I said that once I start, I won't be able to go back. But I kind of distracting. I'm just, let me see. Cool. Yeah, once I start, I can't go back to the meeting. So try your best. I'll give you all time. I'll try to give you all time. I'll give you like 15 minutes. All right? So just note that if I start, it will be kind of hard for me to go back into the meeting. But anyway, so the back EMF equation. That's the first thing you have to know this equation by heart. Please, I beg. So EA, which is your back EMF, is equal to 5, and I'll give you all the variable meanings just now, over 60 E. So this is your back EMF equation. This is one of the back EMF equations. You could get some derived equations from this, but there's a default or fundamental equation for everything. So we know E is the back EMF, right? So phi F is called the flux per pole. So remember, this is your field. So this blue, these two bars that creating this red current going across, this red flux going across, that is your field flux. Yeah. So you have a flux being created per pole. Yeah. Because a pole by definition is a north and a south. Because you need north going to south. Okay. So if you had another pole on top here, and I'm not drawing bad, but that's the concept, and north to south, that will also create another current or another flux going from north to south. Yeah, but most of the time the poles are uniform, so that's why they say the flux per pole. All that is, a north and south is a pair. If you have another pair, they want to know the flux per pole. Cool. Oops. And that is your 5, which is just the flux due to the field that the armature turning in. So the second thing you need to know is P. P is just the number of poles, if you have to guess. Right, so we reach phi F, Z, well, and it's just the RPM of the motor. That's all that is. RPM, rotations per minute of the motor. We reach P, Z, Z is the number of active conductors. They will give you this value, okay? You don't need to calculate this unless they give you enough information. You don't need to calculate this, okay? As was the number of active conductors in the armature specifically. I'll show you what the armature is, just so you all won't get too lost. And then A, there's something called the number of parallel paths. And let's have a catch it. So you have two types of windings in terms of how we could actually wind the motor itself. So the first one you could have is lap winding. And if the question says it's lap wound, the A will equal to P. So basically, number of parallel paths will equal to the number of poles. Okay, and then the second one is wave. And wave winding, the value of A will always equal to 2. Yeah? So something to remember. They will give it in the question. You will know what it is. They will state it in the question. They have to state it in the question. Otherwise, well, I'll tell you that. If they don't state certain things, they kind of hint and say that you can't use a certain equation. Yeah, because you could only use the equation based on the information they give you. If they don't give you enough information, you just can't use that equation, which is the beauty of knowing all the equations. So no matter what they give you, you could go wherever you want to go. Right? So I think that was, well, 60 is 60. I don't know what, 60 by definition is, remember, is per minute. So if it's rotations per minute, you need the 60 there. Okay, so I don't need to put a definition for that as a constant. Okay, so these are variables, you need to know them, and you need to know this equation by heart. So it's one of the most important equations when it comes to a DC motor. So it literally lays the foundation for everything else. Okay, so let's take a detour and let's just run through the different types of configurations. And we'll go back through some equations for you all to know. And that should be it. Right. So you have three, I think it's three types of configuration. So you have the separate. So if you all did the lab, I think you all did the lab. In the lab for the DC motor, you all use separate excitation. So meaning that your field winding, the voltage for that was supplied by a separate source, and then the voltage for your armature was supplied by a separate source. So you call that separate excitation. So you call it excitation. The configuration is based on the excitation type. And all excitation is how you power your field. how does the field get the power? Does it get the power from a separate source? Does it get the power from the same source? How does it get that power? It depends on the configuration. Okay? So the first type of configuration we know is separate. So we call it separately excited. So if it's separately excited, you have two voltage sources. So you have this first voltage source is going through a resistance. Why? Because think about it. Your field is copper wire, which means if you pass current through copper wire, you get a resistance. Copper by definition is a resistance, right? RF is always larger than RE. Yeah? Because with RF, the reason for that is something called inductance. I'm not going to in depth, but all it is, the more coils you have, or the more turns you have, is the stronger the magnetic field induced will be. That's all it is. That is why the RF will be high, because you want more wire. So you add more coils, and by definition, if you add more coils, your resistance would increase because you're using more copper. You can't make like a tick 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 copper. That wouldn't make sense. You can use hundreds of coils or turns to create your RF. RF is always larger than RE. And that's resistance. Then you have a coil. This inductor modeling the magnetic field produced. So you have your little magnetic field there. And then now you have the armature part of the circuit. So you have your EA. So this EA is actually turning part. So this actually turning. Yeah. So that's the armature. Cool. And then you have resistance RE. RE is very small because with RE, remember you're trying to, the more current you have is the better for RE. So how do you get more current? By having a small RE, because the more current you have is the stronger the induced magnetic field will be here to cut it. Yeah, so just opposites based on application. But you don't have to worry about it. RE is less than RF. And he need a source. So we just give it a source. So VT. And has basically separately excited. So this RF, we can say this phi F will cut here, and he have two separate sources. I would call it separately excited because the excitation is separate compared to the armature. So you're supplying the armature and the field with two separate sources, as all it is, and the same operation. But what this gives you the ability to do is you can actually vary your field flux, and if you could vary your field flux, you could actually vary the current, which is what you all did in the lab. You'll actually vary the IF, which if you change IF, which is the current here, you'll change phi F. Because if you change the current going through the coil, you'll be changing the magnetic field created by the coil. And if you change the magnetic field created by the coil, you're changing the back EMF. And if you change the back EMF, it will just turn slower. Or if you increase IF, it will just turn faster. Because it's turning in a stronger magnetic field. So just visualize it, okay? You just have some that coil turning in a magnetic field. If you increase the strength of the magnetic field, it will turn faster. If you decrease the strength of it, it will turn slower. That's all it is. Don't overcomplicate it. Yeah? Before you actually overcomplicate it, just make it super simple and then add stuff onto that. Okay, if you try to understand the complicated parts first, in the exam, you will get the easy part wrong. Where the way life is. Okay? Understand it's simple first and then scale it up. So they're separately excited. So you have your IA, everything flowing nice. So from this circuit here is where you get the big boy equation, which is VT. Your supply voltage is equal to your back EMF plus the voltage drop across R. Reason being is this is a loop. So by definition, I don't know if you all know KVL, I'm not sure, but all it says is the sum of the voltages in a loop must add up to zero, or it must equal to the source. So the voltage drop across this RE due to I and the voltage induced due to EA. When you add both of these up, you should get back the supply voltage. That's all this is. Yeah. Well, it's separately excited. The other configuration you all will need to know is something called shunt. So shunt exciter is basically a fancy way of saying parallel, which is what you all did in the lab. You all did parallel. Reason being, shunt does give you the ability to do something called self-excitation. So you don't need the this VT here for IF to get the phi F, just using the same source. So let's do that. So you have VT. And the first place it was split to in parallel, you have RA and you have EA. And then now in the circuit itself, you also have your RF and your phi F. And this is your input current. This is I and this is IF. Yeah. And this is basically parallel. So the same input current that you have here from the source, it's supplying your back EMF, which is the part that's turning, and it's also supplying your field. And will be no IF, will be more, will be less based on the resistance. How we know this? Because R is very small. So by definition, a smaller resistance will attract a higher current. Cool? And vice versa with the resistance. Right, so we have this. This is shunt. What this allows you to do is something called self-excitation, which you all did in the lab. So I won't go too in-depth into that. If that come in an exam, will be a theory question, okay? But you're just using something called a residual voltage in this magnetic field here, because there's a magnetic field. So this little magnetic field here, when you actually turn off the motor, it will have a little residual flux. And that residual flux, when you power back on the motor, this will just flow in this direction, and that little thing here will give you a little current, and when it cuts, remember there's a magnetic field. So when this little magnetic field cuts this EA here, it will actually create a back EMF. And once that back EMF started generate, you have everything working. And now he will give you more current this way, which would then give here more current, which will make this magnetic field get stronger, and it will just continue to cycle through. It would be a never-ending cycle up to that point, that is. So all the residual fluxes is just you could use that residual flux to excite the motor. And you don't need the separate source to do that excitation. Okay? And these are the two configurations you will need to know. Series, you wouldn't bring series in an exam. And compound, you don't need to know. Compound is basically a mix of shunt and series. That you don't need to know that. That's outside the scope of the course. Most likely. If it was outside the scope of the course for us, it would be outside the scope of the course for you all. So that is master's level theory. So all you need to know is separately excited and shunt, mostly shunt. Because that is what you all got tested on in the lab. So most likely that will be the question that he will want you to know. So you're going to be one of these two, right? And the equation for VT, this part here is the same thing. Both of these are the same. The only difference in this circuit is that the input current is equal to the sum of IA and IF. VT is still the same in both of these branches because it's in parallel. So you could calculate what the current is in each branch. Yeah? That is the only difference. Yeah? And that is the two configurations that you need to know in for exam, that is. Right? Any questions on this? Alright, cool. So know how to draw it, obviously, know how to draw it. This lays the foundation to do any question. I'll show you all these steps with. But for transformers, DC motors, synchronous induction, anytime they give you a question, always draw the equivalent circuit and plug in the values that they give you. What I would do, it lays out the entire floor plan in front of your face so you can know what you don't have and what you have, to then use what you have to get what you don't have. But if you don't know what you don't have, you can't get what you don't have. Yeah, that is how it does work. So if you can actually see what you have in a circuit and the positions it in, especially for transformers and DC for to some extent, it help you out a lot. Like a lot. Okay, you can see everything in front of your face. Cool. Alright, so let's move on. So the next thing we need to know are important equations. Memorize this by heart. Just memorize it. Okay? You just need to memorize it. Know the ins and outs of the equation. Please know it. Because you don't have time to be thinking and twiddling your thumbs in the exam about what equation to use. Memorize the equations, especially for power. Yeah? Or any course that is. Memorize the equation. It's basically the bread and butter for the entire course. Okay, so let's go through. If you could print this page or write it down, do it because it's really important. So the first equation that we went through is the EA equation. So we know EA is equal to phi n ZP over 60A. That's the first equation. The second equation, I'll call it a 1.1 earlier too, is to go from RPM to rotations to angular velocity, obviously angular speed. The angular speed is just omega m. Yeah? So the equation for this is omega m is just equal to 2 pi on 60 and you multiply it by n. This n is rotations per minute. So you're going from rotations per minute to radians per second, or whatever unit this is. I can't remember the unit, but I think it's radians per second. Okay? So just know the conversion, because some equations you need the value for omega n. So you will need to convert it. Some equations you can just use n, but most equation is omega n. Cool? And from this, you end up with another equation. So if you actually do a little bit of manipulation of this equation here, so you can kind of do this on this side in red. The red parts, just know it's just a derivation, right? So if you transpose this equation here, for n, you end up with n is equal to omega m 60 on 2 pi. And then if you just plug this value of n back into this here, for this n here, that's making a substitution, the 60's will cancel, and you'll end up with the equation 2, which is EA is equal to phi omega m ZP over 2 pi by E. Right? And then this now, majority of these variables here are constants. So we could pull out these stuff that are constant. So we know P as a constant, Z is a constant. Unless you go into the motor and yank out copper wires, this not going to change. A still not going to change, but 2 pi is a constant by definition. So what we could do, we could pull out those constants. And when you pull out those constants, you end up with something called K, Ka or Kf, which is called the motor constant, which is equal to Zp on 2 pi A. So this is 2.1. This is just called the motor constant because there's a constant based on the motor. All these are parameters given in the spec sheet of the motor. So when you buy a motor, it gives you what the Ka value is. So you can use it to do other calculations. But in the exam, this is the equation for it. So if they ask you to calculate Ka, most likely they will have the values for each of these, plug and play. But as I say, you have to know what the equation is. Okay? And once you pull this out and you replace it with Ka here, you end up with the second equation for Ea, which is Ea is equal to Ka phi omega m. Yeah, so there's our next equation for your EA. So far, you have two ways you can actually calculate what your back EMF is. You have this equation, which you have N and Z and P and stuff, and you have this equation that has Ka in it. So when you read the question, if they ask you calculate Ka, based on what they give you, you calculate Ka with this. If they don't give you these values, it only have one more equation that you could use to calculate Ka, which is this equation here, which means they would have given you these values already. Yeah, so it's just knowing where you are and where you have to go to. And well, we went through this equation already, so this is your motor equation. So your Vt would equal to your back EMF plus the high that this will never change. And from here now, it gives you how to calculate EA given your supply voltage. So you can kind of connect it in your head. If this is EA, you have EA here. Well, this one is kind of a derived equation, so you really have to know it. Because there's just a segue in between. And you have this equation up here for EA. So with these three equations, anytime they ask to calculate EA, you should know how to calculate it because the equation doesn't change. And they will give you enough information to calculate it. You just have to know, as I said, what they give you. And if you know what they give you, you will know what equation to use because you memorize the equations. Yeah? So let's keep calling it. Cool. So we have Vt is equal to EIRA. And then next popular equation. The name of this equation is called the power balance or power torque equation. When you will use this, anytime you start to talk about torque and power and I'm going to think any question, yeah, this is what I'm trying to tell you. Alright, so this torque power equation, you have two types of torque power equations that you will need to know. So you have the first one, which is the electromagnetic torque, and then the other one is something called the output shaft torque. The shaft is basically just a piece of iron that's sticking out of the motor that connected to the armature. That whole thing, the part that's turning, that is your shaft. Yeah. So that shaft there actually has a power. And then the electromagnetic torque is something different. So how I think about it, this electromagnetic torque is before you actually try to move the load. This is just the torque before, right? So this is called the induced torque. This is before you actually try to move the load. This, however, is the torque you need to move the load. It's two different torques, right? So don't mix it up. So you call this one TE and this one is T sharp. You will know what they're asking you for because they will use the same jargon. They will say calculate the electromagnetic power or the electromagnetic torque or calculate the output shaft torque or the output shaft power. They will use the same jargon, so you will know which equation you have to use. Okay, and it's the same equation, that's different variables. So the equation for this one at least. So it's EA is equal to TE omega M. By definition, this is PE. E means electromagnetic. Okay? So PE is equal to TE omega M. That's the general equation, right? P is equal to T omega. That's the equation we're using. So if you're using it on the electromagnetic side, the PE will equal to TE omega M. Or, which is the beauty of the equation, you could calculate it by multiplying the EA by IA. Yeah, so that's basically the first one, right? And from here, there's 6. And based on the equation, this EA we actually had a nice equation for EA up here, which is K phi omega m. So we can actually get another equation. We replace EA with that one, so we get PE is equal to KA phi omega m IA, which is the same as TE omega m. So it is 6.1. Yeah. So this is the first equation. PE is equal to TE omega m. The EAI part, just remember this. Once you remember this, now you just plug in the EA equation with K phi, and then you put this other equation. So technically, you have two ways to calculate the electromagnetic power. You could find it with the K phi MIA or the TE omega, and vice versa. If that is to calculate the TE, you could just transpose the equation and get whatever you want. So it could go anyway. Okay. Now, well, this equation here kind of suffix. So P sharp is equal to T sharp omega m. So the P sharp or the P out, just by definition, just your horsepower. So it will give you a rated horsepower. So you can kind of get the P sharp from that. All you need to do is multiply the horsepower they give you in the question by 746. And this will give you a P sharp in watts, which should need to be in watts due to SI units. So this will always give you output power. So don't mix it up. Once you give you a horsepower, you can actually calculate. Let me just answer this before it irritates me anymore. Dismiss. Cool. Yeah. So yeah, so that is your output power, which is your P shaft. Your shaft is your output, which is the part that you connect any load to. And well, T shaft, just the torque of the shaft, which is the torque you need to actually move the load that's connected to. And well, omega m is just the speed of the shaft. Yeah? So that's basically your power torque equations plural. So that's known as this equation. It's really the same equation. P is T omega m. It's just electromagnetic path is before your losses, and this one is after. So it's just two different terms. So this is after your losses. Now this one is before. Where the losses coming from is that, remember, the shaft heavy, or relatively heavy, right? In order to start to turn that with the load connected to it, you actually need power. So the first thing you actually have to overcome is the torque you need to actually turn the shaft. And once the shaft started to turn, then the load connected to it, yeah, and that's it, and that'll actually give you your output torque. Because if you don't overcome that torque, the motor just not gonna spin. You'll just hear it going and nothing gonna happen. I think most people kind of mash up a fan before. Like when the last fan mash up and you put it on one, you just hear it vibrating over and over. Yeah, that means that the torque that it getting is not enough to actually move the load. So the electromagnetic torque is not enough to overcome to actually move the motor. Yeah, if you just see it vibrating, nothing gonna happen. Which means the fan either need cleaning or it just mash up. Too much friction in the motor. So it can't overcome the load at all. Right, I think okay. Yeah. And that's basically the equations you need to know. I think I have any more. When you reach the output, I really only need to know efficiency. We knew what efficiency was from transformers. So by definition, efficiency is basically output over your input. Anytime you forget what it is, and in terms of which one going on top or the bottom, your output will always be less than your input because the output is after losses. Your input will always be more because it have no losses in it. So this here will actually give you the two waves. So your output power, you know this is your horsepower by 746. That's not going to change. Anytime you need the output power, HP by 746. You know that for sure. It's a known value. The input power now, most of the time you can't calculate your input power, but you will have your output power. So you can calculate the input power by just adding the losses back to the output. Okay, if you add the losses to your output power, you'll basically get back your input power. So that's basically what you do. These losses, if you look back at the circuit, these are real losses, which is I squared R losses. So the two I squared R losses is basically losses due to the two resistors you have in the circuit, which is your RA and your RF. You only have two real losses. So your losses by definition will be something called frictional windage. So your losses is equal to your IA squared RA, because power is I squared R, plus IF RF, and plus something called friction and windage. So this friction and windage is basically you trying to overcome the friction, because metal and metal rub. So you have to overcome that friction. And also when windage is just in the atmosphere outside, if you're actually trying to turn a load, when you're trying to spin something, you actually have the atmosphere there that actually preventing it from turning. So all that is just lump that entire thing into something called friction and windage. Losses due to those. Yeah, and then well, I squared RA and your IFRF will basically give you your internal losses, and this is our external loss. And these are internal. Yeah. I think that is really all we need to know in terms of equations. Yeah, that's all. I think I have one more. Yeah, I think that's it. Well, let's make sure. Alright, so that one. But I kind of told you already before, but I didn't really specify it. So, your rotational losses. So, any question, I might ask you for the rotational losses. And that's basically your electromagnetic power, which is basically the induced power. Remember, that is the power before any rotational losses. Yeah? And minus, well, plus. So if we carry it on that side, it will be, oh, sorry, I mix up the two. Right. P of minus PE. Yeah? So basically, this P out here is your 746 by HP, the horsepower, and this PA is the induced one. And the difference between these two will be your rotational losses, which is basically just the losses due to you actually spinning the motor shaft. Right? Now, from here, you could
So
try.
that PO
Yeah,
is the
yeah,
same thing as the P shaft?
correct.
Okay.
Because the shaft is at the output, and they will
Right.
always give you what your shaft power is. So when they give you the shaft power, remember, power is the rate of doing work. That's by definition, right? Well, we all did thermal and stuff. So the power is the rate of doing work. Different sizes of motor will do work faster than others. So if it's a small motor, which is a smaller horsepower motor, it will actually do work smaller, do less work, more less efficient. But a bigger motor will have a higher horsepower, which means that for the same torque, obviously it will be able to spin faster because it's a higher horsepower. All the output power is basically how efficient you actually gonna do work, which is the rate you're gonna do work. Some motors just do work faster than others. So logically, this rotational losses for larger motors it will be bigger, but the ratio will still be the same. Yeah, because the PU will compensate for it. Because obviously, in order to turn a larger load, you will need a larger electromagnetic power. Yeah, so and the losses, but it will scale, but it will be the same. But it will be relatively high because it's a bigger motor. Yeah, but yes, your output power will always be horsepower by 746. That's the conversion ratio. And well, PE, PE is TE omega M or EAIA, multiple equations that you could use to calculate the value for it, which is why we went through it before. Okay, so there's a cheat sheet. Like this is a cheat sheet. These 8 equations here, well, not really 8, but roughly. So these equations here basically will lay your backbone or your foundation in terms of everything you need to know for DC motors in terms of equations. When you read the question, which is a different skill by itself, once you read the question, you will know what they give you, and you just use them what they give you to get what they want. That's all it is. Yeah, if you don't know what to do with either one, you don't know equations, which means you don't know how the equations link together. Okay, if you notice, these equations, most of them are linked to each other. Because there's one EA here, omega m, you plug it into this one, you get the next equation. Then this equation here, if you know it, you can plug it into this one to get this equation. So they are kind of, they linked. So once you memorize it for a period of time, you could go anywhere. Like, it's literally endless, right? Um, that's basically it. So I'm gonna run through one more thing and I'm gonna run through the tutorial. So sometimes it will give you a question where they like change something, which you see in the tutorial question. They will make a change in the circuit. Most of the time the changes they make is they will change the flux. Yeah, they will always change the flux from the questions I see. Right? Anytime they change anything in the circuit, most of the time the speed will change. So they will always ask you to calculate the new speed. So yeah, that's how to see the link between the different stuff. So I'll just run through the link here, and when you do the question, you will kind of see how it comes together. So if you change the flux, first off, kind of visualize it, right, guys? So you have a, let me use a separately excited. So yeah, flux, I'll draw it up. So you have your RF flux. There's your phi F here, and your RF, and you have a current IF going through the circuit. You have a EA, which is the turning part of the motor, RA. You have your supply VT. So current actually going in the opposite direction this way. Okay, so you have your currents this way separately excited. So on this side here, you have voltage giving you current, giving you phi. Cool. On this side here, you have a voltage giving you IA current, which going through there, and you're giving you a magnetic field on the armature. That magnetic field on the armature cutting the magnetic field due to the flux or the field, and that interaction, Fleming's left-hand rule, giving you a little rotation, and we'll start to spin. That is all, and how would I start, right? So if it's spinning, and I was to change this phi, whether I increase it or decrease it, I can actually control the speed, which is that type of motor speed control technique, the varying the field. So if I change this, the first thing that will actually change, if I change phi is EA, because the back EMF is due to this relative change. Remember, something cutting, and that cutting, the EA reversing or trying to prevent that induced EMF due to the cutting. So if you have less cutting, you have less things to oppose. And if you have less things to oppose, your EA will drop. And if your EA drop, your speed will drop because you have less induced voltage, which means that it will just spin slower because you have less force to work with. Yeah. So that's how the cookie does come to. So if you change your phi, to change phi, you need to change IF, obviously. Remember, the current and the flux is directly proportional to each other, right? How do you decrease current? Well, if it's a circuit, you just increase the RF resistance, right? But which is impossible, but it is possible if you have access to the terminals in the motor, which you do sometimes. So basically, you can break the circuit here and bring our next circuit, a power resistor. So this open circuit here, and this will be RF plus R add. So you're basically just increasing the resistance of the field. And if you increase resistance of the field, your IF will drop. And if your IF drop, your phi F will drop. So that's how this part has happened. So if you change phi F, IF will change. right? And then from there now, if these things change, phi changes your back EMF EA, which went through that just right? So your phi changes your EA. Then if your EA changes, EA changes your IE, because these two things are direct proportional to each other, right? So these will change basically from the equation EA VT minus IARE. Yeah? Direct proportions are stretch plots. They're on the same line, so they will have the same ratio. Okay? And then from there now, if your EA change, based on the definition, your speed will change. How I know the speed will change? Because you basically have an equation that states that EA is equal to phi n ZP over 60. So if your back EMF change, your speed will change because of this equation here. Okay? So the steps, all you need to do, one, you calculate your new phi, phi. That's the first thing you do. The second thing you do, you calculate your new IA, new. And that IA, the equation fits by definition would just be KA, TE, I think it's TE and KA. Yeah. And then once you calculate your new IA, you will just calculate your EA new. For this one, I'm not give you all that. I feel I might. I'll give you all stuff that I had to derive. So I'll just give you all the flat equation. So it'll be 2 pi A T on Z P phi nu. Just to keep it simple. So when you calculate your phi f nu, you just basically plug it into this equation to calculate your new IA. And then once you calculate your new IA, just calculate your new EA, which will be VT minus your IA new RE. Okay? By definition, once you have EA, you can calculate your N. So you calculate your new speed. So calculate N using your EA. So EA is equal to phi NZP over 60 A. Well, by definition, we can get that value. And if you need to calculate the speed in omega m, you just use the conversion ratio that the omega m is equal to 2 pi and 60 by the speed in rotations per minute. So if the question asks you for the speed in radians per second, you just use the conversion. So that's basically the steps when they change the flux, which is majority of the time what he does bring. So the steps, calculate your phi f, calculate your IA, calculate your EA, and then use the EA to calculate your speed. That's the steps in a nutshell. So yes, memorize the steps, but also once you do the questions and you're familiar with the process, it does become easier. If you try to read this and memorize it, it's not gonna work. You actually have to like implement it in the questions, and once you become familiar with it, then you master it, which is what I'm trying to say. Cannot cram for this because it's too much for you to put in your head in a short space of time and try to remember everything in the exam. There's 4 topics: transformers, DC, induction, and synchronous. Once you do 2 questions well, you pass most of the time. Right? 2.5, well, you're on your way to get an A based on the weighting of the questions. Alright, cool. So that is the end of the theory part of it. So now going into the questions. So before I do the questions, do you have any questions on any of these? Oh, you're all good. Cool. So I look to do the tutorial. Cool. So do one. So that's the two tutorial questions because everything else kind of repeats after that. Cool. So when you read the question, they will give you, obviously, they'll give you the information that you need in order to do the question. So 30 horsepower, which means they give you the P out already. They give you VT and they give you N. Shunt, so you know it's in parallel. They give you poles, which is P, and they give you phi F, because flux per pole. The armature has 882, so this is Z. And well, 4 parallel paths, which is basically your A. And at rated speed, and they give you IA. So that is basically everything that they gave you. And from there now, once you understand what they gave you, then you start the question. And everything here from here will just be plugging into an equation. So the first thing I want is the back EMF. So looking at all these values they give me like phi and P and A, Z and N, that I could just use my default equation for EA straight off the bat. So EA would just equal to phi NZP over 60A. So in this case, it will be phi, so it will be 0 0.025. Let's plug in all the values in no particular order. 882, and I divide that by 60A, and at the end you'll basically end up with 340. And I plug and play once you know your equations, right? That's all it is. Based on values they gave you. Right? B. You couldn't use EA is equal to VT minus IA RA. Because remember, VT is equal to EA plus IA RA. So if you transpose for EA, you basically end up with VT minus IA RA. You can't use this equation. Yes, they give you VT. Yes, they did give you IA, but they never give me what RA was. So I can't use this equation to calculate A. If they did give me what RA was, then yeah, I could use it. But the only equation I could use based on the values they gave me was this one. Yeah. And second question, the power developed in the motor. So that means is the electromagnetic power, which is PE. And we know PE is basically TE omega M, or is equal to EA IA. Then I look at what I have. I just calculated EA and they gave me IA already, which is the 67. So therefore I could just use this form of the equation. I can't use this because one, I'm not going to calculate M to be omega M, and then TE, I don't know what TE is, so I can't use that as yet. Most likely the other question, or the part C, will ask you to calculate this, which will be easier because you already calculated this. So anyway, PE is EA IA, so EA is 340 and the IA is 67. So you end up with 22.78 kilowatts. Yeah, straight off the bat. Just using the little equations we know and the questions that I asked it for. Yeah, that is all it is, straight off the bat. Part C, what I asked you to do. So, oh wow, calculate the electromagnetic torque. So the electromagnetic torque from this equation here, if you transpose for TE will basically be your electromagnetic power divided by your omega M. You already have this P, cool, but you don't have omega M because right now the speed is in RPM. So you have to convert the RPM to radians per second. So we just use our little equation. So this is 22.78 kilo, which is by 10 to the power 3, divided by omega M. So it will be 2 pi on 60 multiplied by the speed, which is 1850. Yeah, so have everything we need. And once you plug that into a calculator, you'll end up with 117.56, well, approximately. Right? Well, when I did my calculation, I probably didn't get exactly but it's around the same thing. So that is the electromagnetic torque. I remember this is your torque before your rotational losses, right? So just remember that. So if they say calculate the torque before the rotational losses, they're basically asking me for TE. Anytime they're talking about the output part, the way they'll use the word shaft or output or useful torque or something like that. Okay? Right, rotational losses straight off the bat. So we know from the definition the rotational losses. So P, friction and windage, is your output minus your P. Right? So let's see, well, by definition, let me see if I derive this thing. So your output power will basically be TE minus your rotational losses, friction and windage. So let's see if I derive that correct above. Right? So therefore, your TE by definition, PE, sorry, not TE, your PE, electromagnetic, will basically be your outputs plus your friction and windage losses. Okay, so cool. So this equation here, if I try to make this the subject of the formula, will end up being PE minus PO, not PO minus PE. Cool. So plug and play. So we kind of just plug in into the equation. So we have the 22.78 kilowatts, and the PO will be 746, and your horsepower, the horsepower was 30. Yeah, I'll plug and play, and I end up with 395.81 watts. So this is basically what we're trying to do. Just write out P a little better. Cool. And the last question, calculate the shaft load from the equation we have from before. So we know the P shaft is equal to a T shaft by omega n. So basically, the T shaft, which from the question is your shaft load. So your T shaft is your shaft load. So this here is your shaft load. It would have to be a P shaft, which is your P out, divided by omega m. So this here is your horsepower. And your horsepower is 30. Yeah, 30 by the 746. And well, the omega m will be the 2 pi on 60 by your speed and RPM, which is 1850. Okay. And that there, once you place in a calculator, should end up with a 115.52 newtons. As load, so will be newtons. And that's basically the power flow. Yeah, straightforward question, but this basically is the concept. So the concept is read the question, write down everything they gave you, like all the variables, write it down. And once you write it down, you know what you're working with. And once you know what you're working with, then you look to see, okay, what are they asking me for? Once you go to what they're asking you for, that is where your strength and knowing your equations comes in. Once you're strong in your equations and you know what they gave you, you could get anything you want. Because it have no magic about it. It's either you know the equations with the values or you don't. It have no in between. Yeah? So straight off the bat, straight off the bat, straight off the bat, straight off the bat, and straight off. Just plug in and play. Nothing we did here was um, trying to manipulate anything. It's just know your equations. And based on what I gave you, you can calculate anything. Okay? And that's the first question. Okay, so cool. So that's the last one. So then the eight. This was number 8, and this was number 7. Yeah. So I'm gonna scroll down. I think I'll put it in here. Cool. So same concept by using the same steps. So first thing I do, I read the question. So they gave me horsepower, which is my output power. So I know I have that if I need it. They give me VT. They give me N. They give me P. Armature conductors is Z. Then they said the armature is lap 1. So remember when we did lap 1, A will equal to P. Yeah, by definition, right? And for the other type, which is the wave, the A will equal to 2. So that's basic example of them giving the type of winding you have. So this lap is equal to P, which is 4. So A is equal to P, which is 4. And this circuit has a resistance. So the armature is Ra. Cool. Rated speed, the armature current, also, yeah. The armature current's Ia, so there's 100. And the field resistance, which is Rf, is 135. Cool. So they gave me good better values. But the one thing they didn't give me is like the rotational losses, which is okay. So I have a good better values that I could use to calculate what I need to calculate, which is okay. So the first thing I want to calculate is the TE. So we know TE, we only have one equation to calculate TE. So TE, by definition, you can use the same equation we did on top. This one right here, same. But we write it down. So let's write the power form of it first, and then derive rule. So we know PE is equal to TE omega M, which is basically the same as EA IA. So we know this. So let me look back to our question. We don't have TE, so we can't use this form of the equation. Which, if I can have TE, I can't use this equation. So I know this entire equation gone. I have this one now. I know I have IA, but the question is, can I get EA? Yes, I could get EA because EA, so VT is equal to EA plus IA RA. And in the question, they gave my IA, they gave my RA, and I know what VT is. So I can calculate what my EA is. Yeah? So EA will basically equal to VT minus IARA. Yeah? So let's calculate one time. So it will be equal to 250 minus the I, which is 100, by the 0.18 for RA. And you end up with 232 volts for the back EMF. So, I mean, at that point, you can calculate where your PE is. So, your PE will equal to EA, which is your 232, and you multiply that by IA, which is 100. Yeah. So, we have that. So, let's see what value. That'll be 23212 watts. And I mean, at that point in time, once you have PE, you can get back your TE. Yeah, because you just can't use this equation straight up. So now that you have PE, you can get back your TE. So transpose, so it'll be PE, which you already have before, divided by speed in omega. You could have used this equation of it, but you still wouldn't know what PE was. But because you know the two forms, you know you can calculate the PE from here, and by definition, you know you can calculate your EA from this. As I say, all the equations linked. So once you know them, you could always use them if you need to use them. Right? So this will be 23200, and omega m, same thing, 2 pi and 60 multiplied by the speed, which is 1150, and that will give you 192.6 newtons. Right, so that's quite a little different, but same concept. Once you write down this equation, you obviously know you can't use this first. You should realize you have IA. EA, you shouldn't get flustered because it only have two equations to calculate EA. Well, actually three if you're trying to be technical. But based on what they give you, this would be the easiest one to use to get the EA, right? I don't know if you have enough equation to use the other one. The phi, no, they never gave you what the flux was. So you can't use that equation. Yeah. Cool, and I part A. Part B, the flux per pole. So the flux per pole base you're asking for is phi F. It only has one equation that has all those things together. So the equation we're using is the EA equation. So E is phi NZP over 60A. So all we need to do is just make phi the subject of the formula here. So you get phi F is equal to EA by 60A all divided by PZ N. Okay, let's make it the subject of the formula. And you go ahead because remember we just calculated what EA was from before, which is the beauty of the question. So you end up with 232. 60 A is 4 because A is equal to P for lap. Oh, this is 4. Z is, I think it was 1200. Well, we know the N is 1150. When you plug that in a calculator, you should get 0.01 Weber's elevator squares, right? And that's 5 calculation. You only have one equation most of the time for 5 based on what they gave you, right? And well, the other one is the rotational losses. It's the same concept, same equation actually. So we know the pre-frictional windage rotational losses is PE minus, yeah, P out. Okay? Now we know this is 746 by a horsepower, which is 30. So it'll be 746 by 30. And you calculate a P from before, which is this. So everything kind of coming back together. So you'll end up with 23200 minus the 22380. And we end up with 826 watts or 20 around there. According to if you round up or round down. So that'll be your rotational losses. The equation for your rotational losses is always the same thing. It never changes. So from the time you see them, so rotational losses, write down the equation. Most of the time, if they're asking you for this, you either have to calculate what PE is, because you will have what PO is, or they will have asked you to calculate it before, and you just have to plug it in. Yeah, so it's kind of, that's all that matters. Right, D, efficiency. So we know the efficiency equation by definition is your outputs divided by your inputs. So we kind of have to manipulate the equation to get it into output because the only thing we know for sure is the output power. Yeah, so it'll be P out divided by your output power, and you just add back your losses to get back the input power. Yeah, so this will be 746 by 30. That will give a output power. Same thing for the bottom first piece. And the losses, you only have two losses. We have I squared R losses. So we only have two resistors in the circuit. So the first one is your IA squared RE and your IF squared RF. Okay, so you already have those values from the question itself. Okay? So if you look back in the question, they gave you all those things already. Everything is right in the question. Okay? So once you plug in, so obviously on a space here, once you plug in the IA and the RA from the question and the IF and stuff, you will end up with the efficiency. The value of it will be the same as the question. I think I'd get 87.85. Yeah, you only have two type of losses. So based on the question, you will know which one you're working with. Okay, cool. The last question is the question for E. So let me see what I asked it for. Alright, shaft loop, same. That usually never going to change. So T shaft will be a P out, where P shaft divided by your omega m. So we know the P shaft is 746 by 30, because we know the P shaft is your output power, and omega m is 2 pi and 60 multiplied by your speed in RPM, which is 1150. Yeah, now once you do that, you get power. By
So
shaft. Yep.
I have a quick question for the
Yeah.
IF. They had give us that.
So anytime they don't give you what it is, just leave it out. God, I don't think they gave you enough information to calculate what it was. Yeah. But if
So for the
mm-hmm,
losses part, right?
mm-hmm.
In the efficiency.
Okay, honestly, I say, yeah, you can calculate it. So remember, right? Honest, I see what I say. I didn't state that before. So if you
Yeah.
have a circuit, right, you have a resistor here, and you have a resistor here. So this resistor here is RF, and this is RA. Yeah, they gave it this as 100, which is okay. But remember, you have the voltage here, a little bit of circuit analysis, right? So the voltage in parallel is the same, the current is different, right? So in the question, it said this was 250, and they gave you RF of 135, and well, they already gave you what the IA was, right? So all you need to do to get what this IF is, IF would that's equal to the VT divided by RF, and that is the current you will use in the efficiency equation for IF, right? So that's what I was talking about.
Yeah, yeah.
Yeah,
That
so
makes
that's
sense.
yeah, cool. Yeah. Same if you didn't have the IA, same thing, because you know the voltage and you have R, so V is equal to IR, I will equal to V and R. You can get the currents. Yeah. So cool. Good question. Good question. I think I
So,
stated that.
quick question again. So,
Yeah.
for the losses, wouldn't you include the ground edge?
If they state it, most of the time they will kind of tell you what it is, but in the question itself, the internal losses have to do with the efficiency of the motor itself. Your frictional windage losses what to do with the environment that you're in. You understand that, right? So like if you operate the motor in like Antarctica where the place cool and the atmosphere just thick, your frictional windage losses will increase. But then if you operate it in like the equator where the place hot, you will have less frictional windage. So in the question, they will state if they wanted to consider it. So in the question, if I give you a fixed one, you will consider it. So that's based on the question, which is a good question. So if you want to, you could put the frictional windage, but what you could do when you do any question, because I didn't put this in and I get the answer that's so hard. But you can try and put it in and see if you get a different answer. Okay, you're not wrong technically, but the frictional windage losses have to do with the external losses, not really an internal loss. Yeah? Because the efficiency of the motor is the motor itself, which is everything to do with the parameters the motor have. Yeah? This is more of an external loss, which changes based on the environment. Yeah? Alright, any more questions? Alright, cool. Alright, part F. So part F is the part where they change in the flux question thing. Right, so the shaft load on the motor remains fixed. Okay, but the flux is reduced. Fair. The one here to calculate the new operating speed, which is exactly what I told you they will bring, right? That is most of the time what they will bring. So it's the same steps. You have to calculate your new phi based on the ratio they give you. After you calculate your phi, you calculate your IA. Once you calculate your IA, you calculate your EA. And once you get EA, you get N. Same four steps. It never changes. Cool. So I run through that one time. So F. Step 1, we need to calculate the new phi. So phi new will equal to 0.8 multiplied by a phi old. So I believe the old phi was that was by 0. Where did I calculate that? Yeah, 0.01. So if you multiply that, you end up with 0.008. So that's a new 5. So like 1. Step 2. So let's have an equation that links the electromagnetic torque with the IA. So luckily for us, since TE is directly proportional to phi IA, if you change, remember the TE, they said in the question that this staying constant, right? This staying at 5. So for example, if this was 10, this is 5 and 2. If you increase this to 5, this will have to decrease because you're trying to keep this constant. So whatever you do to 1 in terms of the phi, the I will just do the opposite. Yeah? Because the set, the TE is constant. Yeah? So in this case, the set that this flux dropped by 0.8. So if this dropped by 0.8, this will increase by 0.8 to keep the same ratio. Yeah? So basically the current increased by 0.8 of its previous value. So it'll be 0.8 by 100. Well, in this case, it will be 1.8. So, yeah. So when you do that calculation, you end up with the IA to be 125. The easy way to do it, if that kind of confusing you, is the IA new, which is equal to the IA old multiplied by phi old divided by phi new. Yeah? And once you plug in the values into that, you end up with 125 because the phi old is the where's that 0.01 and the new 0.08. So you end up with this as the value. And you have I. So the next thing you need to calculate is the EA new, which is VT minus your IA new by RE. So you end up with 250 minus 125 by 0.18. And you just end up with 227.5 volts. So that's step 3. Step 4, you calculate your N using the EA equation. So when you transpose for N, you end up with EA new by 60A divided by P, which is number of poles, by phi new, and Z, which is everything you have from before. So it will be 227.5, which is a EA new, 60, well, you know, A is 4, no, P is 4. You have phi new 0.08, and his Z was 1200. Now once you plug in all that, you end up with the new speed to be 1421.8 RPM. If the question asks you to convert it to radian per second, you just multiply by 2 pi and 60. Alright? And that is it. Like if you could do those two questions, especially number 8, in terms of the process, you'll be okay. Everything else is basically using different equations to get the same thing. You have 3 EA equations, you have one equation for the output, you have one equation, or technically 2 equations for the PE, the EI, or the TE omega M. Everything else is just one equation for the rotational losses, and everything else is just constant. So with that knowledge, you could comfortably do majority of the DC Moto's questions, because there's a moto, which means the parameters they give you, as I said, equations, variables, and you could get anywhere you want to go, any question. Alright, so stop the recording.